In this video, I'd like to talk a little bit more about dot products, and more specifically the projection component of the dot product. Now, we defined the dot product of two vectors u dot v to be the magnitude of u times the magnitude of v times the cosine of the angle in between. And we could also reverse these components because, again, multiplication is commutative. So we might think of this as the magnitude of v times the magnitude of u times the cosine of the angle in between. And they mean the same thing. Now, the reason why I say that is because we're going to consider the math that's associated here. One of the magnitudes times the cosine of the angle in between. If we think of that as a separate computation, that's essentially what our projections are. So verbally, we would say the component, that should sound familiar to you, the component of vector u in direction of vector v is defined to be the magnitude of u times cosine of theta. And similarly, we could say the component of v in the direction of u is defined to be the magnitude of v times cosine theta. So as far as a visual representation goes, here's what we're trying to show. Let's say we've got an object that's moving in the direction of vector v, maybe a car that's moving uphill or something like that, a cart, I should say, that's being moved uphill. And at the end of a string, some child might be pulling on the cart. Well, they're not pulling on the cart directly parallel to the vector of travel, but maybe they're pulling at an angle because of the angle of the handle or the string that's attached to the cart. So the question becomes, how much of this force, when being pulled in this direction along vector u, how much of that force actually is getting applied in the direction of travel? Clearly, there's a lot of force being pulled at this angle, but some of that force is being directed upward and perpendicular to the surface, and some of it is being directed forward in the direction of travel. We're putting in a lot of force to pull at an angle in order to get this object to move forward along the path. Well, it's the adjacent side of this right triangle that tells us the length of this vector arrow, and as it turns out, the length of that vector arrow does give us the amount of force or velocity or whatever unit of vector that you're dealing with in the direction of vector v. And that's what we mean by the projection of u onto v. How much of u's vector is actually being placed in the direction of v. And another way to visualize that, you'll sometimes hear people say if you had a light source that was shining above your vector u and it casted a shadow directly down over top of that vector u, well, how long would the shadow be against the floor that's represented by vector v? That's another way to think of this projection when we're projecting a light or a shadow against a wall. Personally, I like the trigonometric definition because it's, to me, easy to see that we're dealing with a right triangle here. And when we're concerned with the adjacent side length and we have the hypotenuse side length, because we have the magnitude of u, when we have the hypotenuse and we're looking for the adjacent, to me that screams cosine, and cosine is definitely part of the definition that we've been using so far. Now, if I use that cart analogy in this diagram over here, that also holds true. What's happening is this cart is rolling uphill, but maybe it's moving too fast, or it's gone up the hill, and we're now pulling on the cart in the opposite direction. Again, our handle or our string is not, being pulled in the same direction or a perfectly opposite direction of the cart, but it's being pulled at a particular angle. So what portion of that force that's being pulled at that angle is actually pointing in the direction of travel, or in this case, the opposite of the direction of travel of vector v? Well, again, we're going to multiply the magnitude of u times cosine of theta. Since theta in this case is greater than 90 degrees, you'll notice that the cosine computation will come out to be a negative result, which is a good thing, because the force in this direction is the opposite of the force that's being applied in this direction. And the signs do matter. Now, if that description makes sense to you, if you start to understand this notion of projections, then that might help you understand the work calculation that we were doing in the last video. In those notes, we just blindly stated that work is equal to the dot product of force times distance. But what we're really implying here is that we would like to know the force, the amount of force that's being applied in the same direction of our distance of travel. And even though the force that we're applying may not be in that direction, the dot product will account for that and will determine the amount of force that's being applied in the direction of travel and multiply that by the distance that the object does travel. In this example, the force vector is pointing in the exact same direction as the distance of travel or direction of travel. So that's nice to see, but it's not always going to be that way. If we jump down to the example at the end of this series of notes, you can see exactly that situation happening here. We have a man that's pulling a cart that started at the point 0, 0 and ends at 100, 0. So we could say something like this, that the distance vector is equal to 100, 0. It has a 100 horizontal component, but a 0 vertical component. If there was at all any incline, we could account for that with the rectangular vector. Now, as it turns out, the handle on this cart is not parallel to the direction of travel, so only a portion of this gentleman's force that's being applied in this direction will actually go in the same direction of travel, and this is the component or the projection that we're after. So if we read through the instructions again, we see that he's pulling with a 20-pound force at a 60-degree angle, so the force vector, the magnitude, is 20 pounds. And the angle is equal to 60 degrees. So if we'd like to compute the work, we've got a couple options here. We know that the work is equal to the force vector times the distance vector. And one definition said that we could take the magnitude of force times the magnitude of direction and multiply that by the cosine of the angle in between. Well, we know the magnitude of force, that was 20 units. And we know the magnitude of direction, that's 100. That one was easy to see because this was a nice flat travel, so we'll multiply that by 100. And cosine of 60 degrees is the angle that we're dealing with. And using the calculator off screen, 20 times 100 times cosine of 60 is equal to 1,000. And we were dealing with pounds of force and a distance in feet, I believe. Yep, a distance of feet. So we will say that the unit of measure here is 1,000 foot-pounds of work. Now, alternatively, we could have taken the polar coordinate form of our vector here and turned it into a rectangular coordinate because the vector of f times cosine of theta, the magnitude of f times cosine theta and sine theta will also convert this into rectangular form. So if I took 20 times cosine 60, I end up with 10. And if I took 20 times sine 60, I'd end up with 10 times the square root of 3. And I'm using precise answers here because this 60-degree angle is a nice position inside our unit circle. The cosine value at this position is a half, so half of 20 was 10. The sine value at this position was radical 3 over 2, and radical 3 over 2 times 20 gave me 10 radical 3. Now, with the rectangular component of force and the rectangular component of, the rectangular form, I should say, of the distance vector, we can also find the work that way as well. Again, work is defined as the force vector times the distance vector. And when we use component notation, we would need 100 times 10 plus 0 times 10 radical 3. And here again, the result ends up being 1,000, and our unit of measure for work is foot-pounds. So either technique will lead us to the same answer, provided that you completed the technique correctly. And to finish this video, we'll go ahead and back up to the example that we've got here. And actually, we'll go ahead and finish the notes now that we've seen that projection in action here. And to be consistent with the diagrams shown with these cars, we're going to say that the work vector is the sum of the u vector plus v vector, where the u vector is the vector that's parallel to the surface. In this case, we're talking about a driveway. And v is perpendicular to the driveway. Sorry, I said work vector. I was stuck in the last example. The weight of the car, I should say, is equal to the sum of the forces, the resistance to the rolling force, and then what we call the normal force, perpendicular to the surface of the driveway. Those two sum together to equal or match the weight of the car. So vector u, depending on how steep your driveway is, you can probably imagine that the vector u would be greater the steeper the incline is, because vector u is going to represent the force that would tend the car to roll down the driveway. And vector v, which we often call the normal force, is the force experienced by the surface of the driveway, and that's perpendicular to that surface. The magnitudes of these forces are the components of W along U and V. So if I were to project W in the direction of V, let me use a different color here to make that stand out. If I was going to project W in the direction of U, or if I was to project W in the direction of V, those are the components that we were just addressing a moment ago using that work formula and the dot product. Now in this particular example, we're not actually computing work, we're not using the dot products. This is more of a statics problem where the vehicle is remaining still, it's not moving. We're just trying to compute how much force is being experienced in both of these directions, in the u vector and the v vector direction. So if we're going to answer question A, the magnitude of the force required to prevent the car rolling down the driveway, well, the rolling force that we're experiencing here is the length of vector u, and so we need to calculate that, and we can do so by imagining the triangle that's built right here. Now it's upside down from our current perspective, but if you rotate your paper, hopefully you can see this. But in question A, the length of u is going to be equal to the length of w, the magnitude of w, 3,000 pounds, times cosine of 75 degrees. And I recognize this because cosine of some angle is equal to the adjacent side length divided by the hypotenuse. We know immediately that our objective is to solve for the adjacent side. That's what our u component is describing. So if we multiply both sides by the hypotenuse, then we will isolate adjacent. And that's exactly what we have here. Hypotenuse times cosine of the angle measure. And that computes to approximately 776 pounds of force. For part B, the vector, I should say magnitude. We should put the magnitude bars around here. The magnitude of vector v is done the same way. We have a 3,000 pound force that acts as the hypotenuse. And we've got the vector v that we're going after, which is acting as the adjacent side length of our triangle. And this is a right triangle with an angle measure of 15 degrees. So we want 3,000 times cosine of 15 degrees. And that result comes out to be a number close to 2,898. So we didn't actually compute work here, but we did compute projections for this example, and we did compute work for for this last example down here. And in the process of computing work, we did require the use of projections. So I hope these examples help you better understand what's happening here. I do recognize that this is a brand new concept, so it's a very good idea to take some time and watch some additional videos on your own. Certainly you can find some on YouTube, and you can always, of course, email me or send me a message through Schoology for extra help. Thanks for watching.